Welcome, everybody, to today's Sendo Reliability webinar. This is Fred Schenkelberg. And Europe, Eitan, the Netherlands, welcome. Yeah. The topic today is kind of a deeper dive into something I mentioned last month when I was talking about building a reliability plan. And one of the things that Carl and I noticed is that when we were working on our book and the steps to build a plan, is one of the things we did in each of the examples we were using is we just knew, somehow we just knew that this is the right technique or method or tool to use. And we stopped in one of our discussions. This is, how did we know that? How do we go about doing that? So we spent quite a bit of time in discussing and sorting out and breaking down what is the process to actually pick the right reliability method. And I hadn't seen anything else that really talks about that. There's plenty of resources out there that have all kinds of how to do this, how to do that, how to do a halt test, how to do an accelerated test, how to analyze data, all kinds of cool stuff about how to do what we do. And the hard part is that we've got a lot of options. Which is the right one to use for a particular circumstance? And how do we know which is the right one versus not the right one? And so part of this process is to what I want to talk about today is some of the insights or ideas that some are common sense, but some are exposed, hopefully for the first time. Well, not if you've been listening to these webinars or joining us for these discussions, or a member of Ascendo, you've probably heard many of these topics before. But the idea is that we need to step back and think. And I think Chris Jackson likes to say is we don't check our brains at the door when we go to work. We still need to consider and think and analyze and so on the decisions that we're making. And when we're building a reliability plan or recommending a course of action, that requires thinking. And we'll get into that here in a moment. So the core of this, and hopefully it came across last month also, is that what we do as reliability professionals, and when we use reliability activities or methods, like running an environmental set of tests, for example, or doing stress testing or analyzing data, is we're not doing that just because we like doing it, although I do really like breaking things. And so I kind of go out of my way to do that more often than I probably should. But the idea is that we're creating information, is that we're taking, whether it's prototypes or a stack of data, and we're doing something with it so that we have something we didn't before. We're putting it together, we're analyzing it, breaking it to find out what's the failure mechanism, for example, and that's information that we can use to make improvements. Now, most of the information that we generate is used for people to make decisions. The classic one is this ready to ship? If I'm developing a product, is it ready? Is it good enough? Yeah, does it meet our range of expectations and criteria? Now, that's a decision that the team and often the program manager or whoever's running the program needs to make, to say, all right, we're good enough, let's ship it. And the risk is that it's not ready and we have a horrible high failure rate, and worst case, we recall and shut down that product line. More often is that there's a lot of uncertainty around that decision. Are we there yet or not? Is it good enough? Now, we only have limited prototypes or modeling or various activities we use to inform that decision. And so there's always going to be risk. Yet part of what we do is help inform that decision, at least from the reliability point of view, the quality point of view. Is it good enough from those aspects? Now, plenty of other things go into the decision, are we ready to ship, like marketing and supply chains and all the other aspects of bringing a product to market. but we do have a role in informing those decisions and informing the people making those decisions. And so that's a key piece in creating a reliability plan, but also in deciding for us to select an appropriate method. The idea is that appropriate, when I break that down a little bit, is, well, what are we able to do? What's our capability and lab facilities and measurement capabilities and knowledge about failure mechanisms or not? What can we do and not do well? But also, what is the limitations? And we'll get into more of these constraints in a bit, but if I make a recommendation for something that we would all have to go off and get a PhD in some arcane stack of knowledge for 4 or 5 years before we can even hope to start the set of experiments we want to run, well, that's a constraint that many programs really can't afford. So many of you heard about my very first experience in reliability, where I was asked to run a set of tests to prove or to show that this new product would last for 20 years. Well, I had no idea what accelerated life testing was. And the constraint is you have to come up with a plausible experiment and results that show it one way or the other within 6 months. And I said, well, now I got to think about this, and did some research, went to the library, did all that kind of stuff, and found Accelerated Testing book by Wayne Nelson, and thus started my career. But the idea is that there's a time constraint. The customer needed to make a decision in order to commit to purchasing this new product we were developing, and the key piece of information they wanted, among all kinds of other things, I'm quite sure, which I wasn't part of those discussions, but it was, will it last for 20 years in our environment? And that's a constraint, and that was informing a decision. So it shaped what kind of evaluation or testing or modeling types of activities I did in order to help that customer make a decision. Now, another part is that we've got a bazillion different methods. Carl and I decided to call it methods, is tools and techniques, everything from hypothesis testing and control charts to Pareto diagrams and Weibull plots, and on and on and on and on. And we've listed these in the appendix of our book, the ones that we found that were most commonly used in our experience. And it's pretty broad ranging. There's lots of different options. Now, part of it, the trouble is that if everything, there's the old adage of, if you really are good at one particular tool, let's say, like in my case, at one point, I was really enjoying designing and running accelerated life tests. And so what happened was that people knew that, and they would come to me from different parts of the organization saying, hey, can you help me run this experiment, set it up and design it? And it was an accelerated test. And so for a while there, pretty much the only thing I did was accelerated life testing, knowing full well that on occasion that this really didn't need an accelerated test. There's other better methods to use. And the hard part is breaking away and realizing that there are alternate ways that can get as good or better result within the set of constraints, and or more cost effectively than running a full-blown 3 stress level accelerated test. And so as I matured in what I did, I often looked for those alternatives and tried to make recommendations for a course of action that use the appropriate method for the fit within all of the capabilities and constraints in order to get the information we were looking for. And so that was part of an evolution in my career. And part of what I want to talk about today is how to shortcut that, so you don't have to wait 40 years to figure out and gain all this experience, but how to step through it in a methodical way so that you can improve your ability to select the right tools. Now, the hard part here, and this was a boss of mine at one point when I recommended an accelerated test way early on, he said, what are the other options? What other courses of actions can we do, and why are we not selecting them? And I thought, I hadn't thought of that. I kind of landed on this idea of an accelerated test, and it seems obvious to me, but yeah, there are other ones. There's all kinds of different ways to get to this thing. And so we had a discussion about what the other possibilities were, and ruled out most of them pretty quickly because of the constraints, but we also enhanced the option we wanted to use or decided to use because we gathered a lot of other information from some of these other techniques and methods in order to help us run this accelerated test much more efficiently. So whenever you're faced with an issue or a problem, you should run this little tape in your head. Did you consider the other options? And why is this one the one that we should select? If you should be able to articulate that very, very clearly. So now let's focus in a little bit on just the decisions part of this. Part of the process of creating a reliability plan, and you may or may not be involved with it, but there's so many different decisions that are being made in the development of a program or in the operation of a production line. Part of it is what are those decisions? What's the nature of those decisions? Are we making comparisons? Two vendors is a classic one. Is this change to the production line making an improvement or not? And how do we actually make that comparison? Are types of decisions that we're making, and we would pull a range of different tools to answer those things. But consider that you're starting a new product. You have a new platform or a new, say, type of pencil or marking instrument, and how many different decisions are involved in the creation of that? And it's from texture to color to size to shape to length, weight, on and on and on. And then there's all the things about durability and legibility and all the performance criteria, which is about where we start getting involved as reliability professionals. As well, how long can that marking instrument make marks that are legible and to the quality or width or depth of color or texture of line, all of those different kinds of things. How do we get those so that all of those decisions are made? Most are probably made pretty unconsciously. Oh, I need to figure out a length for it. And if I make it 4 feet long, it's pretty hard to wield with a hand. If I make it 6 inches long, it's, reasonable to use. But what's this? Is there a standard? Is there what are all the inputs that go into this? The idea, though, is that a good many of those decisions of texture and materials and quality and all the functional aspects of the performance of whatever device we're making or using, they impact reliability in one form or another. And reliability in the large sense includes, does it meet the customer's expectations, right? Not just that it has enough ink to write a whole novel, for example, by hand, and I imagine that might be a criteria for somebody. But the idea is that, is it meeting their expectations? Does it last long enough doing what it's supposed to do and doing it well? And so all of these different design-related decisions or production-related decisions often impact the performance on a reliability aspect of the product. Now, I would dare say there's thousands and thousands of decisions that are made that impact reliability. And so part of the process is identifying those decisions. And where are they? Who's making them? And how important are they? Those are all aspects of what we do. And part of this is paying attention during meetings. It's part of it's interviewing key people in the organization. Part of it is querying folks what information they need so they realize that, oh, I need that so I can make this decision, prompting people to think through what do they actually need in order to make a better decision. And there's no lack of decisions. That's usually not the issue. Once you start looking for them, you'll find them all over the place, right? But then it becomes, how do we prioritize them? We can't. Well, I don't know that we can't. I think it's not economical to spend a ton of money doing all kinds of different activities and generating tons of information for every single decision. Some decisions are more important than other ones. Now, some of them our program manager might say, hey, I need to know if this is going to be good enough to ship. Here's our reliability objectives. Are we there yet? Or are we close enough that I don't have to worry about it? That might be a direct requirement placed on us to generate that information. But there's also important types of decisions. Do we pick this vendor or that vendor? Or do we pick this technology or that technology? Do we use this architecture versus another architecture? Those are critically important to the overall performance of the product, including its reliability performance. Identifying those, and we often talk about being involved very early in the product life cycle, because that's often where the most important decisions are made. You know, what market are we going after? What problem are we trying to solve? Those start to shape the reliability expectations and eventually the reliability performance. And we start getting into material sets and architecture, a lot of the reliability performance is already starting to be locked in. The other end of the spectrum is, let's say you're working on an electronic system. Well, we're not going to be able to be involved with every component selection on every circuit board. Even a simple circuit board might have 20 or 40 components on it, but some of the larger ones have thousands of components. Each one is selected for its performance, but also its ability to survive that environment and survive it and be robust. So concepts like derating and stress strength analysis come into play, but we're not going to do that for every electrical engineer or mechanical engineer. So the idea is to set up guidelines or rules of guidelines or suggestions or best practices. And so derating guidelines or stress strength calculations or safety margins, policies, provide a set of information to as many of the engineers as possible. And that, coupled with some training of why it's important and why we do it, then transfers a lot of that actual generation of information or informing so many more decisions, is probably a better way to say it, in an effective or efficient way. So things like lessons learned and best practices and guidelines is a way to get to as many decisions as we possibly can. And there's circumstances where it's a unique decision, so we have to create unique information. But other times, selecting a capacitor to handle a 5-volt load, that might be made a number of different times. So providing a guideline is an effective way to go about doing it. Now, I'm going to pursue an example all the way through today's discussion. So let's say we're looking at a new technology, and I'm going to keep this industry agnostic as much as I can. But the idea is that when and it's a product that is going to go into a power supply, and that there's been identified a problem during the startup. Think of it as an inrush current is causing damage and limiting the lifetime of this particular device we're working on. And so we've come across a technology from somebody that says, hey, we can help you mitigate that problem and solve it for you. And it's like, okay. And it's not anything that our team is terribly well versed in. We've heard about it. We've seen the sales literature, and we've just gotten a couple of prototypes in, and we're going to check it out. Now, one of the initial concerns is, because of the lack of knowledge around it, is, will it last long enough in our application, in our use? And so the decision comes up in one of the meetings is, well, if we need to know if this is going to work functionally, which we think it does. And two is we need to understand, is it going to last long enough to meet our reliability expectations and reliability goals? And then we need to know this, we need to make a decision in 3 months. Otherwise, we have to move to another type of solution or live with the problem in order to make our timelines for getting this product up. And so that frames a basic problem, which is very realistic. I run into this a number of times. Hey, we got this new thing. If we have the resources, some teams would try 2 different technologies. We'll enhance the old one, or we'll try this newfangled thing, and we'll compare them and contrast them over the prototyping period and see which one we lock in. But these timelines generally have ramifications for supply chains, for the final design shape, for the ability of that to be incorporated into the overall system, for manufacturing setups and processes, for maybe the maintenance of the system in the future, on and on and on. So it's usually not just reliability, but that drives that timeline. It's often that it has to meet, we have to make a decision so we can lock it in and build the product effectively. So that's the problem we're looking at. And we'll look at a couple more bits of information before we dive into what we could do to solve this problem. You may already be thinking of a couple of ideas here, but let's see what we get after the next round of topics. So I think I covered this already, so many decisions. I don't know anybody that's counted it, but I do know that it's many more than we can possibly individually address. And so triage or prioritization and a judicious use of guidelines really is a way to approach getting to as many of these decisions as we can. All right. Now, just about, I think I've told this story a gazillion times. I was asked to help create an accelerated test for little plastic zip ties, the little strands of plastic that were notched on one end, and you slide them through an opening that's also keyed, and you can pull it tight and it would stay there. And it's used oftentimes for holding cables in place. And so this is the only time that they said, well, you can have as many samples as you want, because we can buy them by the thousands, and there's 3 vendors we're getting them from, and they're slightly different, each one. So you can have 1,000 of each one or more if you want them. They're fractions of a cent each. You can have as many as you want. On the other hand, we only have one Instron machine to do the pull test to test tensile strength of these things, which we've correlated to why they fail for us in the field. And it was like, okay. So even though I can have as many samples as I want, if it takes us 15 minutes to measure each one in a destructive way, I really can't reasonably expect technicians to do 24/7 pull tests for the thousands of samples I have. And so we had to think that through a little bit. So that was one example of this thing. But we had an Instron, right? We had that equipment. We had a technician that knew how to use it and do pull tests and was pretty good at it. And they actually had done a gauge R&R and had really narrowed down a good way to measure this. They had already done the characterization work, knowing that the pull strength or the tensile strength of these units was related to how well they performed in the field. The question I got brought into is, well, we're going to age these. Because the polymers oxidize and they become less able to withstand the loads that they have. And so we're going to age them and then measure the decline in its capability over time, its strength over time, and then pick one of the vendors that maintain the most strength for the longest period of time. But we had a lot of ways to do this stuff. We knew how to do it. We had the chambers to age it. We could run pretty much an oxygen rich environment over these things to or accelerate the oxidation rate. We knew it was a chemical process, so we could increase the temperature. We didn't use pure oxygen. We ended up using just a oxygen rich normal air, and then accelerated the temperature, which allowed us to use the Arrhenius equation. And it worked pretty well. But the idea is that we had the equipment, the skills, and everything else. Now, if we didn't know how to measure these things, if we hadn't done the characterization work and sorted out a good, effective way to make those measurements, then that would have been a constraint. But here we had a lot of strengths, so we naturally went to those. Now, many, many times I've run into organizations that have a lab or a set of chambers, and they might have a vibration table and a handful of other pieces of equipment and microscopes, and sometimes even really nice, high, very expensive capital equipment for analyzing materials. But oftentimes they don't. And that runs into a constraint. If they didn't have an Instron machine, now we could go rent one. It might be the right tool to use. But would there have been other strengths, other ways that we could have evaluated it that we were already good at? So taking a look at what we're able to do, and are they able to understand the design of an accelerated test? Many of us have run into teams that, they talk about halt testing, but they say, well, of course it failed. You overstressed it. We're not going to do anything about that. Well, there's a lack of knowledge there. So that's a constraint that may require some education to overcome. Now, other teams embrace halt and know it fully well. They understand the concept. And so that becomes a strength for them. They understand that we need to figure out how this thing fails, or what are the failure mechanisms are likely to occur. Then they're going to say, well, we already know halt, and that's a good fit. There's a bit of an issue there, though. If you're really good at halt and that's the only tool you use, it goes back to my earlier story about when I started doing accelerated testing all the time. Every problem looked like an accelerated test to me. If you're in an organization that only wants to do halt, they may miss the opportunity to do something else that would more better. I'm thinking of my English teacher in 6th grade, would benefit them and add more value if they considered other tools or techniques. So it's that process of guarding yourself from always picking what you have, because it may or may not be the appropriate method for what you're trying to achieve. So limitations. We almost never get enough samples. I like that one story about zip ties because I ended up with thousands of samples, but I was still limited because I didn't have the budget and available technicians and multiple Instron machines to do all the testing that would be required from all of those samples. Now, I mentioned early on, is in this example we're talking about, there's a timeline. We need to have more information than we have right now in 3 months. We need to answer this question: is it going to last long enough in our environment? And we need that information to decide whether to use this new technology or not in 3 months. But we also need to ask the question, well, how precise do you need to be? Would an engineering judgment work? Should we go talk to a handful of subject matter experts on that technology? Should we pull up some literature? Should we, what kinds of information, how I want to say precise, but how accurate? If we need to know that it's 20 years plus or minus 1 year, that's a different problem than if it's, will it last at least 2 years with less than 10% failure rate, which is a very different criteria and opens up a variety of different ways to answer that question. And then also budget. If we wanted to buy 200 more Instron machines and hire another couple hundred technicians to run it, well, that might have broke the budget, might have been limited by budget considerations. Even if we were going to just temporary hire a bunch of folks and rent a bunch of equipment, that starts to get expensive. And is it worth getting that information for the cost that's involved? So this cost benefit trade-off comes into play as a constraint in nearly every time we have to decide what we want to do. And so and there's many others. There's tons of other limitations. All right, so let's go back to this example. So the vendor that has this new technology, it's a little module that fits into a power supply, and they said, oh, there's plenty of them. They're not terribly expensive. You can have a bunch to do your evaluations. And so samples were reasonably available, say in the order of maybe 50 to 100 would be available if we wanted them. But then we also built on the capability that we knew how to measure the problem. And so we had a pretty good technique then for monitoring if this new device was actually working. Would it mitigate or eliminate the problem that we're seeing, this current inrush type issue, for example? And while we could measure it, part of it is how well does it do it? How precise is it? How accurate is it? Are we missing a voltage spike, for example, that might solve one problem, but introduce a different problem? Was it capable of measuring the effects of electrostatic discharge, if that occurs? And what kind of damage would occur with that? So there was a handful of things that, as we started diving into this new technology and what question we wanted to answer, we started having lots of discussions in the team as saying, what do we know and don't know, right? And part of it is, which is key in selecting a method, is we don't really know how it fails. And the vendor gave us this device and said, nobody's ever asked us for a model for how to time to failure thing. We did a parts count prediction and said we added up all the components and said it's got, 28 fit, which was pretty meaningless for our discussion because we knew that it's going to be under stress. Given the circumstances of our system, it was going to be under stress. And we wanted to make sure that we didn't have a wear out mechanism or a weakness in it, that it couldn't handle that stress. And one of the benefits, another thing to take away as we start narrowing down what kind of technology or how to evaluate this, is that it's only used in the power up process. In our product, think of it as in a solar array that it fires up in the morning and starts in that. It's once a day that it gets turned on, or it could be a server, or it could be whatever the technology is. But we have the benefit of it's only used once a day, and it's only used for about 10 minutes. And then it goes to steady state, and this device then essentially is offline. It's quiescent and hanging out waiting for the next day. Now, what would be one of the assumptions that goes into that it's used once a day? And it's a critical thing to think about. And I should have stopped earlier to ask more questions, but use the chat. What would be something to consider if we're trying to pick a way to do the testing or modeling or evaluation of this system, if it's used once a day and it's used for about 10 minutes? What else would you need to know? Well, yeah, Brian, it would start up cold. That's true. And that's really kind of the idea, is that power supply was starting up time of day. Yeah. Is it cold? Is it hot? Is it preheated? Is it indoors? Is it outdoors? We probably have access to a lot of that information. But how about the failure mechanism? Does this unit only fail when it's actively engaged, or like the dashboard of a very old car I had, fail when it's just parked in the sun, independent of how often I use it? Will the temperatures inside our device age this new technology or not? Yeah. And at what rate? And sometimes just sitting quiescent may be more damaging than when it's actively used. And so it's something to consider. If we don't really know the failure mechanism or failure mechanisms, and we probably have some experience with capacitors and diodes and chokes and all kinds of other devices that are probably within this device. And there is one proprietary new invention. It's a new type of component, which has given us the pause here. We don't really understand that new technology, but how does that actually work? And more importantly, how does it fail? What are the ways that it can fail? And so that's something to think about, is not just because we only use it for 10 minutes a day. Couple that with we're not really sure how it fails, then that could be a problem. And it's something to dive into a bit deeper and to understand and answer those questions before we select a problem. So we have a bit of some benefits. We know a bit about this thing. We have ways to measure it. We could do better at it, but we also really don't know the failure mechanism. So some of the techniques that many of you may have been thinking about now has probably changed. It's probably an alternate way to go about doing this. All right. Is there an obvious method? How would you solve this problem? Yeah, William's talking about startup stresses are generally worse than steady state operation. That is true. That is true. Many cases, depending on the failure mechanism. Yeah, the operating, and the good news is that if we only do it 10 minutes, what are you thinking there, William, is a way to do the acceleration? What's an obvious method here that many of you would jump to, and then why? Why would that be your choice to evaluate this new technology? Yeah, well, maybe my thought early on about, or idea of get lots of methods to consider may have given you pause here. Yeah, Robert's talking about just speed up the duty cycle. Yeah, let it start up, relax, let it go, cold or quiet again, and then repeat it. It's an acceleration of the duty cycle. All right. Now we don't know the failure mechanism. Right. So halt in ton, that's oftentimes an easy way to go if you don't know the failure mechanism. Yeah, and then do the analysis, figure out what happened to it. Do the failure analysis and sort out what happened to it. Here, I really wish the vendor would be more forthcoming with how it works and doesn't work, but they're hiding behind a proprietary trade secret type of stuff. So that always gives me pause when I'm looking at a new piece of material. All right, a couple of good ideas there. Yeah, all good. All right. So when we get down to actually selecting it, the hard part is that oftentimes when we get to this stage of we know what the problem is and we have ideas of what we know and don't know and our constraints and so on, we often jump right straight to a method. And that's okay if you got the experience to do that. If it's because that's the one that you're most familiar with and you don't really understand the other ways to get this information, that may be detrimental. It may not be. We may be right many times, but it's that 1 in the 10 times that we're not quite right. At forensic analysis, I always love taking stuff apart and doing the deep dive into it, especially when I had a full lab and people that knew how to run it to do the material analysis and electrical analysis and chemical analysis. HB had labs for doing failure analysis that were just amazing. Now, many organizations are for hire that have all these cool assets and lots of experience. They certainly are helpful. All right. So let me ask this question. What other ways, other than accelerating the duty cycle, What other methods could we use? And what we need is enough information to decide, is this good enough or not? Will it last in our environment? Yeah. So Brian, that's a good question. This is the first time we're using this product in this application. And let's say the supplier is relatively new to the market, and their salespeople are quite often going to quote that they haven't noticed any failures, and people have been buying them, and they're having more trouble generating enough production, which is concerning. But then they stop with the information when they say, well, this element here is proprietary, it's trade secret, and it's a black box to us. And they're not telling us what it is. So taking it apart and doing the chemical analysis may be violating the non-disclosure agreement or understanding, but more often than not, we'll probably learn something from it. But that's a good question to ask the vendor is, who else is using it? Can we talk to them? Is their application similar enough to ours that it gives us some credibility that this is a good solution? What else? What other methods? Come on, little brainstorming here. Growth testing. Yeah, it might happen, Mike. The hard part is that it's a fixed module. Think of it as a black box. In growth testing, we often run and get a failure and then fix it, similar to halt, and then run it and keep growing and keep going and keep going and making fixes. If we can get the vendor to work with us on that, that might work really well. What other methods out there? Shape factor, beta. Yeah, Y-base. Yeah, that's right. We don't have a lot of that, right? We got a failure rate estimate based on parts count from the vendor. So we don't have the distribution. Use different loads. That's fun, because then we could try all kinds of different stuff and see what kinds of failure mechanisms, show up. Yeah, run the whole suite at them. I like that idea, because that keeps us busy with doing all kinds of cool stuff. I like that. Plus, we get to break more stuff. What else? Think outside the lab. Which failure modes present the highest risk? Yeah. So if this device doesn't solve the problem that we have, this inrush current that comes into our rest of our system out of the power supply, then that's a problem. Now, I'm just making this device up, so I'm quite sure there are ways to handle inrush current that's not going to create all kinds of questions. But let's say, for the sake of argument, that this is a new technology, and yeah, and the failure mode would be pretty obvious, is that the inrush current, or the problem that we're trying to solve, is still there, and we know how to measure that. So that would be good. Yeah. And it's the amount of output over time. Yeah, if we see that it solves the problem and we run it again and again in doing this accelerated duty cycle, maybe the inrush starts to creep back in, or we see a signal that it's degrading, and that could be attributed to this device. It's a good idea. I like that one, Tom. What else? Outside the lab, what else could we do? The vendor is not providing great information to us. What else can we do? And I like the idea of the forensic stuff. We might learn about material properties or structure of the hidden device, for example. And we could do a literature search. We could go find technical papers that are related to this technology, if they exist. Maybe there's a perfect model out there for this device that would solve our problem for us, and we don't even need to go to the lab and do any testing. We need to look, right? If the vendor's not providing it, maybe they adopted this from somebody else's patent, or they published early papers when they were developing it. Who knows? But if we don't look, it's really hard to say that we could avoid all of the testing because testing's really expensive. In most cases, it's terribly expensive. But if the answer is already in the literature, it's already published someplace, and we can, if we really think it's important, we can reproduce it. those results with our particular device, that really limits the scope of what we're doing. We don't have to do as many samples. We don't have to run it as long. We just need to show that the model works. And so that would be another way to go about doing this. So the idea here is to step back and say, well, what are all the methods that would apply? And so accelerating the duty cycle seems like a pretty clean way to go about doing it. Yet if we knew the failure mechanism, right? And one way to find it is to do halt or run multiple different types of stresses and see what shakes out of it. We could learn something. We have to be careful about the timeline though, right? If we're doing too much characterization work, we'll eat up our 3 months and then we have to run a 3-month test. That might pose a problem. But the idea here is to list all of the different ways of doing it. So let's say you've got a completely different situation. You're working with a team and they've got lots and lots of things they need to address, and they're kind of competing for resources and so on. FMEA comes immediately to my mind as a way for that team to prioritize what they need to focus on and where do they need to put their resources. But they could use Pareto, they could use hazard analysis, they could use urgent and important type plotting and charting. They could do a range of different tools and techniques. And so I recommend that if for any of these problems, come up with, fault trees, a good way to go about it. Come up with as many different methods as you can. And outside even the ones that you're familiar with. Sometimes there's a technique or a method out there that is perfect for this particular situation, but you need to consider it. You need to look broadly. So this is the part where you brainstorm and think outside the box, basically outside of your own lab, and look for ways that could build on your strengths and fill in some gaps of what you don't know, and maybe improve your overall organization's capabilities in an incremental way, but also more importantly is actually get the information you need for this particular circumstance. Right. Of course, then once you got, say, 4 or 5 or a dozen different potential ways to solve this problem, to create the information you need to narrow it down, right? But what criteria do you use? I mean, an obvious one is which ones can actually provide the information to the criteria that we need to provide it within the constraints, and in this case, within the 3 months. So if we're going to do a full-on physics of failure model, and it's going to take 5 PhDs, 3 years to go about doing it, well, that kind of blows the budget for time right out the window. We might still pursue it, might be valuable work in the big picture, but it won't help us make this decision in 3 months. Yeah, doing design of experiments. Still seeing a bunch of different ideas coming in. We could narrow it down using, design of experiments with all these different methods and see which method is the appropriate one. But do we have the time for that? Almost never, or the samples. So we're given all these different sets of constraints. And so the ones that just can't answer the question well enough, let's say, we'll just trust the vendor. That's a method we could use. We could say, yep, the vendor knows their product. And I've heard that so many different times. We know our product. We think it'll work. That is a common technique, engineering judgment. Will that answer it well enough for our needs to make this decision? Talk to other users of this particular product if we can get a hold of them, find them. LinkedIn might be a really good place to go find those folks in your networks. Anybody use this new technology? What do you think? What works and what doesn't work? What have you seen? We could do that if our lawyers will let us talk about this new product development thing. But we need to narrow it down. Which ones can actually provide the information well enough in the time frame or in the set of constraints we have to do it? often narrows it down pretty quickly. Second is budget. Almost always budget comes into play. Or do we have the capability to do it? Do we have anybody that knows how to do degradation analysis? Do we have the tools to do that? Because it's often nonlinear. And so that's different than a Weibull analysis. It's quite different. But so do we have the capability to do that? Yeah, derate it. The hard part with the assumptions is that we need to be clear with each of the methods we're using. What is it assuming, right? If we're assuming a linear degradation model, we're assuming that it's linear, that there isn't some other phenomena that makes it nonlinear, which does happen. Is there strictly a time to failure using an extreme theory? Extreme failures, the first failures in, say, a batch of multiple failure mechanisms. Well, then Weibull might apply, but maybe not. Do we have enough samples or information or details of how it failed in order to use one of these other methods? The other way to think of it is each of these methods is, what if we don't get an answer? Is it able to distinguish between it's good enough or not good enough for our particular criteria? How much inrush can we survive, or how much do we need to knock it down over the length of the use of this product, which sets the criteria for degradation? If we don't know that answer, then degradation doesn't really help. We're just guessing again. So part of it is we get a bunch of different methods and then we start narrowing it down. Many of us with experience do that pretty fast, but I recommend writing it down, explaining it to the rest of the team so that, one, you get buy-in for the technique that we're eventually going to select, but also a understanding of the nuances of the difficulty of entry and providing that information. And so that information, when we do create it, will be, I'm thinking of my English teacher again, rolling her eyes when I would say more better accepted and used to make that decision. Yeah, well said, William. Is we need to know what we know and don't know, and then I would add those assumptions. All right, so continuing our example, our vendor doesn't have data for our particular application. Maybe it's a different a range of, or style or power supply or application or type of loads that it's seeing and so on. Maybe we have a high inductive load and they haven't used that environment, been used in that environment before. So that may be an issue, but they don't have the data. All right. The existing literature, do a quick search, we don't find anything. And what we do find doesn't really apply for this application. Maybe there's lots of 4 or 5 volt power supplies, but there's nothing for high inductive loads. So we got to keep looking. We know that creating a physics of failure model, I often joke that it takes a handful of PhD students years to create a good model. That's not too far off. If an existing model exists for that particular device and technology, that's great. Let's just use it. If it works for the range of the stresses that we're in. But if it doesn't exist, that often takes quite a while to do. And it may or may not be appropriate to do over the long term, but it may not provide the information we need within the time frame. And oftentimes acceleration, when we want to do an accelerated test, whether it's accelerating temperature or a variety of different stresses, we need to know what mechanism is. So one of the ideas was use lots of different types of stress and see which mechanisms show up. Now, that may be very useful if we can run them all in parallel and then understand the failure mechanisms, and we can create models for that. It'll take quite a bit of work. It's probably going to run into budget problems. But if we use, I think what a couple folks mentioned it right off, is increase the duty cycle. Now, the key assumption is that it will most likely be stressed to cause damage and or fail or be noticed that it fails when it's under use. The hard part is that we're assuming that it's the failure mechanisms that we're most concerned about only occur during that active use. And that may or may not be true. So it's something to think through very carefully about how we would go about doing it. If we just started doing, 10 minutes on, 10 minutes off, 10 minutes on, 10 minutes off, one, we may overheat, keep this thing at a much higher temperature than it would normally be at. Or maybe that's how the unit operates, is already at a high temperature when it's quiescent. And so what else could go wrong? So doing that teardown to figure out what materials are in there and would temperature degrade them, that may be a meaningful way to go about doing this. But the idea is start eliminating the ones that are just not going to get it for you. You might end up with one or two methods that then have certain caveats. They may have certain assumptions built into them. Be very clear of what those assumptions are. And then run that past the people that need the information, saying, here's the proposed method. Here's what we think we can do. And here's the accuracy that we can achieve and given the constraints and sample size and everything else we have. And here's how it'll generate the information you're looking for. Will that meet your needs? Right? Because creating the plan is just the first part. We also have to get it done, actually execute it. And many of us know that there's always a cable or a sensor of some sort that we just can't get quick enough to get our test started. So usually some startup issues of running an experiment. But more importantly is that the people that need the information need to understand where this information is coming from, how it was created, creating the buy-in essentially for what the outcome is going to be. And there's a risk, there's a finite risk that this experiment will fail and we'll get nothing. And what is that risk? What could go wrong? And we thought through that. And so part of selecting a method is understanding the benefits of that method or technique, the warts and troubles and hurdles that may be involved with it, and the potential range of outcomes that we'll get. Now, we don't know the outcome until we actually run the test, yet what's the likelihood that we get an answer that's ambiguous, that we just don't know? It might say it'll last 5 years plus or minus 10. Well, okay, we don't really have an answer here. So if the criteria is 5 years plus or minus 2 months, for example, in precision. So being very careful about selecting the method such that it meets the range of criteria we need to address, but also has the ability to create the information to the quality of that information that we actually need. Yeah, minimum operating conditions. It's another thought. Some products fail, but I think there's also the minimum operating conditions. What's the range of stresses that it's going to see? And I'm thinking of like Miner's rule. If I can equate the amount of stress that's applied to the amount of damage that accumulates, then we might be able to create a model that's even more valuable. Yet, without really knowing the failure mechanisms, that's hard to do. And so there's probably a two-step process here. Figure out, to the best of our knowledge, what's the failure mechanisms or class of mechanism, and then which stresses are likely to go. And if it's all related to use conditions, then that accelerating the duty cycle may make the most sense. But as you know, every single circumstance will be different. Every single situation will be different. And it takes thinking through and doing a little bit of brainstorming. What do we know and don't know? Some assessment type activities. How well do we need to answer this question? What's the criteria for the information that we need to generate? All goes into shaping what we're actually going to do. And this is just one problem, one method. When we're working with a development team or we're in an operations system, there's dozens and dozens, if not hundreds, of problems that need information. And so doing due diligence and getting the right information at the right time is the idea. That's why we select what the tasks or the methods, the activities that we do. Yeah, that's a good idea. William's saying, maybe just do some redundancy, have a couple solutions for this, maybe this new technology and have an easy way to use something else, or put them in series so that you have two ways to knock down this issue. So many factors and considerations go into how do we go about solving this problem, but thinking broader often helps us then to know that we're on the right track, and plus get the buy-in that this is going to create the information that we need. And so it's very, very frustrating. I've done this a couple of times where I go off and I think I'm doing a great job with this experiment and gathering all this data and doing the analysis, and I present it and they say, well, you're a week late. We had to make the decision last week. Or they say, well, that's nice, but I don't understand it. I'm not going to use that. That's frustrating. So try to line yourself up so that when you start spending a lot of resources to create information, that you get the buy-in, that people understand and can use the information that you create. Goes back to that. We don't do this just for fun, although sometimes I admit I do, but it's to help other people make important decisions that affect the reliability of our systems. So that's part of it. So there's more details in the book that Carl and I put out, and it came out of, originally we only had 5 steps to create a plan and execute a plan. And at one point we just realized that we were jumping over a very critical piece, is how do you select what tools to use, what techniques to use, what methods to use? And so we broke that down. This webinar is a synopsis of that, but hopefully it gives you a couple of insights that you can use. And I suspect many of you that I know are experienced use some of this stuff or all of this already. And so it's all good. So that's what I've got today. Any comments or questions as we wrap up? We're coming up on the top of the hour. I didn't plan it that way. I was hoping to get more discussion throughout, but once I get started running, I sometimes forget that. All right. Is there a course offering? Suresh, which on the concept of what Carl and I did for the book, is that what you're talking about on the course? Yeah. Yeah, we have talked about it. I think our next task is to get the book published in an ebook format. And then Carl and I have thought about doing kind of a combination of these webinars and articles that we've written and podcasts we've done as a free course to fill in some of the blanks and give it stuff. But then we've actually thought about doing an actual course with lectures and discussion and examples worked out through it and stuff like that. And we have given that some thought. Well, stay tuned. We haven't started it yet. We got a handful of other things on our plates, but thanks for asking. All right, so I'm going to end the recording and hope you all have a great rest of your day. I'll stay in line if there's any other comments or questions.